And thank you for the invitation to contribute to the Royal Statistical Society conference. As you will have gathered, I'm not a statistician, I'm a computer scientist, I'm a simple computer scientist, so my talk is from a computer science perspective, but I hope some of the issues that I'm going to talk about will resonate with you or they will make you think. So this is the outline of my talk. I'm going to try and set up the scene and then tell you a little bit about some of the work that we are doing in trying to understand complex system behavior using the big data, and then how you can go from complex system behavior to the individual behavior, and wrap up with some conclusions. Now, I want to start by showing you this picture. Has anyone seen this picture before? Now it looks like a lovely landscape somewhere with mountains. It's not a real picture, it's an artificial one. This is by Michael Najjar, by his collection of works called The High Altitude. He was inspired by the mountains of Aconcagua in Argentina when he visited, and then he used those pictures that he took there to reproduce indices of the stock exchange markets around the world. Now, guess which one that is? This is the Lehman Brothers evolution of price, stock prices, and that's why you see this sudden drop here. Because this is from 92 to 2008, and basically they ceased to exist in 2008. Now, what you see here are peaks and troughs. And what I find interesting, and some of my colleagues, is, okay, we can see these patterns, but why is it that we see these patterns? So you have these algorithmic traders now in the stock markets, and all they do is they try to predict what the next up or down movement is going to be. But I want to understand, why is it that we see these evolution in the prices in the various stock exchanges? So this is what I call mind the gap. So you have a data set, you have a big data set coming from a stock exchange or any market or any other source, and what you do is you analyze it and you get some conclusions, you identify some patterns, and then you often use these to inform actions and strategy, say in a commercial setting. And most people would stop here because they believe that by identifying these patterns, surely they know enough so that they can inform strategy. I would say that this is not enough, and you need to take it a step further. So from the analysis of the data, you then need to formulate some kind of theory to try to explain why is it that you're seeing these patterns. But even that is not enough, because the next step then is, okay, you formulated this theory, is it really correct? Are the hypotheses that you have incorporated in your theory correct? And for that, to establish that, what we do is we try to build these complex models, trying to model this theory and the hypotheses, and then by using simulations with these models, I'll come back to these, we then try to see whether what we see in the real data, the kind of patterns that we see, we can actually reproduce in these artificial models. So we use a lot of simulations, and when I say a lot, I mean a lot. We can run some of these simulations thousands of times to make sure that we are actually getting data that makes sense and they are statistically valid, or we have some confidence in the data. And it's only then that I would claim you can have some confidence if you have gone through this cycle in taking any actions or decisions or informing your strategy. So this is what we are trying to do. And I will explain how we went about and we performed this kind of cycle, and in a specific problem, which is understanding these patterns that you see in markets, and in a specific market, the foreign exchange market, where you have currencies being traded. So in classical economics, you have some assumptions, and if you talk to economists, they're going to tell you that all the agents, all the traders are rational, they all behave the same, and they have these behaviors, however, which fail to explain what we see in the real markets as happening. The other thing that characterizes these markets is this high volume of transactions. So you're not talking about one bid every hour or every couple of hours or per day. You're talking about hundreds of thousands or thousands of bids. So that's requests for buy or sell. So you have these very high volumes of data, and these present us with additional difficulties. And the way we've attempted to, if you like, address all of these problems in one go is, instead of using these traditional assumptions of economics, go down the route of using what they're called agent-based models. So we model individuals such as traders as being these complex software entities that encapsulate behavior, and they can have different traits and different characteristics, and sometimes we can even endow them with things like knowledge, beliefs, desires, attitudes to risk, and then we can create these simulations and see what happens. So for this study, we were really lucky because we managed to obtain a high-frequency data set. These are really difficult to get because you're talking about markets in which you can get data by observing the prices, but what you often don't get is these trading accounts so that you can see what individual traders are doing. So we were very lucky because we managed to obtain this data set from Wanda, and this included over 147 million transactions and 45,000 accounts. So it's a lot of data. We tried to use this data set to analyze what was happening in the market, and this was over a period of 2 years and a couple of months. So we're talking about a lot of data. So this is about 180,000 price points or bids during the day, so it's a lot. Now, usually when you look at time series, you tend to sample. If you sample in this kind of domain, when do you sample? Do you sample at the end? Do you sample every hour? Whenever you sample, unless it's very, very frequently, that's why these data sets are called high-frequency data, you're going to miss important information. And this price going down of a specific currency or going up, if you have missed it, then you may have missed an important pattern. So it's very difficult to try and work with high-frequency data when you try to deal with them as if they were time series. So you've got lots of fluctuations, and I'll explain to you very briefly how we went about and we dealt with the whole process, because we had the transactions data set, and this was quite large. But within that 147 million transactions, we weren't sure which ones were real transactions or they were being placed by the company itself to check certain things. So we had to go through, naturally, this process of cleaning and filtering the data set, and we ended up with this processed data set. And once we've done that, and we went through quite a rigorous phase to determine that we were happy with the data set that we ended up with. We then performed a statistical analysis on the data to try and identify what they're called stylized facts, so patterns based on the statistical analysis. And some of them are already known in the literature, so we were not breaking new ground there, but we were trying to identify whether we can see the same patterns in our own data set, given the length of the data set and how big it is, but we were also able to uncover new stylized facts. So we went on and we established these, and then once we've done that, we just wanted to see whether we would be able to reproduce the same statistical patterns that we were seeing in the market by creating this artificial model, this artificial market model. So we used for this trading agent, so this concept of you try to encapsulate behavior within a smart piece of software, to put it simply. So we've created a platform, and then from this, as we were running experiments, obviously we were generating new data, and then the next step was to compare the data that we were getting from the artificial market against the real patterns that we were seeing in the real data set to determine whether we were actually getting the same results. Now, again, that didn't take one run of the simulation, that took actually thousands. So instead, as I was saying earlier, of using this time series analysis, we weren't dealing with the data set in this way. We used another approach, which is quite new and quite different from what is being done, what has been done so far. We used what is called a directional change event. So instead of using physical time, we identify events in the data set, and we can identify downward trends or upward turns. It's quite complex, so I'm not going to go through the details, but again, instead of using physical time, you work with events. So you can specify a threshold beyond which the price movement, when it occurs, it actually signifies something for you. So you can say that I've got an event there, and the event can be an upward trend, so you can say the price moving up, or it can be a downward trend. Usually what happens is once you identify that, instead of the price going down, the data as we analyzed it, it shows that the price goes up a bit more in the same direction. So you can analyze these runs into the directional change event, as it is called, and then you have the overshoot event because the price goes a bit further up before it changes direction. So you try to identify these patterns. And again, this is very different from what is being done in the literature. So the kind of stylized facts that we identified had to do with seasonality, because you can see these patterns in the data, and I'll show you a couple of examples. Correlation stylized effects. These were positive linear relationships between different trade numbers and volumes, or numbers of buy and sell executed orders, different quantities of market activities, and finally scaling laws. So these we identified in the real data set. And so what was happening in the artificial market, we were populating this with agents, as we call them. These represented these trading agents, who we had no idea who they were. The data set was completely anonymized, but we were trying to model them as having a number of characteristics. So they were interacting based on this processed data set, and they were buying and selling, and we were able to record the activity of the market over a month at a time, but over a long a number of simulation runs, as I said, quite a substantial number. Now these little entities, I would call them, software entities, they were very heterogeneous. So this goes against what we are being told by economists. Their wealth distribution is not the same. When they trade is not the same. The strategies that they use, we used a very specific strategy based on this directional change event approach, which was very simple nevertheless. All we were trying to do is identify these patterns of up and down in the data. The risk attitudes were very different. We were modeling a very diverse population of traders. And by the way, there's no trader that is going to tell you exactly how they trade. Because if they reveal that to you, then they're going to lose money. So in this kind of work, it's very difficult to get any survey data that will tell you how people actually behave, how real traders behave. And what we were trying to understand is what is actually happening behind the scenes, behind these patterns that you see. The profit objective was very different. Our agents, our trading agents, were able to place this market and limit orders, so they could project into the future and have open orders in the market. And they could place variable order size, orders of variable size, depending on how much wealth they had and what the rest of the portfolio looked like. So we generated that. And as I said, we developed quite a complex platform, and you could manipulate various parameters, and you can run it with thousands of agents running at the same time, different profit objectives. So these are just some, but I wanted to show you some of the results. What we were trying to do is we were trying to see what kind of characteristics do these trading agents have, so that they are able to, so that we can replicate the same results in the artificial market. And what you see here are two lines. The blue line indicates the data as the real data, and these are the seasonality patterns that we see during the day. This is a well-known pattern, and you see two peaks. The first one is when the London market opens and the Asian markets are open, and the second one is when the New York and the London markets are open at the same time. And the blue line is the real data, and the red line is our data. So we were able to come quite close to replicating the data as you see it in the market. Now, we analyzed why. And we ran thousands of simulations, trying, for instance, to make all the agents look the same, use the same strategy, so the characteristics that I told you earlier on, we didn't arrive at them by just running one simulation. We had to experiment a lot, and we had to talk to a number of people about this. So, for instance, if you remove the limit orders, you don't see all the patterns that you see in the real data. If you reduce the heterogeneity of the agents, again, you don't see the same patterns emerging. So it's quite telling that some of the assumptions, as we are being told, they don't actually seem to be validated in the work that we've done. Now, another interesting piece of work that we wanted to see was, now that we are able to replicate the data, is it the case that we need artificial pieces of software that can learn on the market, in the market, while they're running, in order to be better, to make more profit? And what you see here in the A line is the real, in the blue line, the A line is the real data, but the other lines that you see are generated by using different trading strategies. And some of them have been generated by using algorithms that learn. So some machine learning algorithms like genetic programming, genetic algorithms we have used. And the interesting result is that you don't need to learn in the market in order to be successful. Now, this is just an initial study, but it was quite interesting that some of the agents that we used that had this ability to learn, they were actually crashing out. We don't know exactly why, but it's an interesting result that we need to investigate further. So we were able to come very close to the real market data only with this strategy, which is still to be investigated because it's so simple. So the next piece of work I want to talk to you about very briefly, and I'll show you a video, is what we're trying to do with this kind of work is we're trying to understand complex system behavior, like human societies, for instance, or trading markets that are really complex because they consist of individuals and each one is different and they affect each other, but you cannot really predict the whole outcome of this system unless you look at the whole result. So, going further, in the future, you're all holding a mobile phone with you today. You have it in your bags, I'm pretty sure. Now, these kind of systems will be populated by these clever pieces of software that will be doing things on all of our behalf. And we want to understand, what kind of societies will emerge and how we can regulate these societies, because some of these systems will evolve and they will be clever. So we're trying to understand these systems as having cognitive models. And these cognitive models can take on the environment information, experiences, the things like word of mouth, reputation, and they can include all sorts of characteristics that you wouldn't normally attribute to a piece of code. But this is what we are trying to establish. And I'm going to show you a video because what we were trying to understand here, you've all heard of social networks. Social networks work because we all like to associate ourselves with other like-minded people. So people tell you social networks are successful because of this, but how do they emerge? So this piece of work was trying to see how such a network can evolve when you have agents interacting with each other, and I'll show you what happens. You see these different colors represent agents with different characteristics, and they start interacting, so you can see how the network evolves and how they mix. But they eventually start finding each other because the colors indicate that they're similar. So there's a group of blue ones here and a small one up there, but they haven't found each other yet. They haven't been able to connect, but they will. And no matter how many times and with what different populations we have run this, they always end up finding that. And now they're going to stay like this. So we don't seem to like going outside the boundaries as we know them. And this is a principle of homophily. And homophily, as a principle, you can use for a number of applications. Like, for instance, when you go shopping and you go to Tesco's and you swipe your club card, you're being identified as an individual, but behind the scenes, Tesco is using the homophilic principle to do what is called personalization and provide you with coupons. So next time you get your coupons from Tesco or any other supermarket, check the kind of coupons that you get. You get coupons for the products that you like, but you also get coupons for products that other people like because you are similar to them. So they're using this very same principle to increase their sales. So I want to end with saying that we see a lot more data being generated. This is not going to change. This is only going to accentuate in the future. But in order for us to understand what is happening, it's not just looking at data from one perspective. We really need to have a more coordinated and more interdisciplinary approach, bringing different disciplines together to look at problems from a number of perspectives. So that was it.
Very good. Have we got questions out there? We do, hooray.
Your finance model seems to be very good at predicting what you might say is typical behaviour, but catastrophic events are very rare. I don't know if you had a chance to run it for long enough or with enough agents yet are you getting any indication of how frequent these rare events are or how likely they are to occur?
The models as I've described them and the kind of work that we've done so far, what we wanted to do at this moment in time is we wanted to see what kind of characteristics the traders have so that we can see the same patterns emerging in the market, and we are happy that we are able to replicate the same patterns. The next step is then to do prediction, because okay, you can replicate the same data. Can you use this to develop these strategies so that you can see these patterns as they emerge in real markets, so you can predict and you can make profit? So that's the next step. And then the third step is to try and model exactly what you're talking about. So for instance, the kind of crisis that we had in 2008, this is foreign exchange data, so we weren't seeing the same patterns because it wasn't stock prices going up and down, it was currencies. But this would involve a lot more work, because the kind of crises, as they happen, they are not just the product of the interaction within the system. You have other factors that are influencing the whole system. Right now, these are not being modeled.
Okay, so
there is some there is some randomness there in the behavior, but we are really interested in seeing how we can actually use these kind of techniques to predict, or not exactly predict, but at least have an early warning system in place. And this is actually part of our research agenda, because we want to be able to understand why are we seeing these phenomena.
Although making an analogy with statistical physics, in statistical physics you get phase transitions when you get a critical mass of effectively agents just interacting internally, but once you can reach that critical mass, then you get a phase transition. So I wonder if this would be an emergent behaviour you could find in this.
Yeah, that might be.
We've got one. I saw you first, so let's have you there, please.
Surely you have an identifiability problem here, in the sense that your agents are parsimonious agents that just happen to, through your structuring, match the marginal colligative behaviour of the whole market. But I could pose another bunch of set of agents that look completely different than yours, which might be almost as parsimonious, but also fit this marginal behaviour of the whole market. In fact, surely the issue is with real agency, with real traders, is that they're complicated, over-redundant agents It isn't that they're parsimonious, it isn't that they're driven by a single parameter, they're driven by lots of parameters. And I come back to the point that the gentleman I think in red has said. The issue here is whether your models behave in the right way to perturbation, not whether they match the reality. Because I could make a set of models to match your reality, but my models might not match the behavior of perturbation. Yeah? That's where the information is. The information is in how it responds to being hit around the head.
Yes, the kind of agents that we have here, they're not controlled by one parameter. They have multiple parameters, and actually, from what we found, it's the combination of parameters together that enable us to see similar patterns like the ones that are emerging in the real market. The kind of simulations that we've run, they were, as you can imagine, very well organized, because we were trying to identify, for instance, this wealth distribution. In previous works, people say every trader has the same wealth. Is that really the case? As a matter of fact, it's not. Not every trader will have the same amount of wealth to trade with. And when we change the wealth distribution in the kind of experiments that we run, it's not the case that you can see similar patterns emerging if you have the same wealth across all agents. So it's not just one parameter, but it's a combination of things. That's why you need to do this systematic study to identify, okay, what are the key elements? Now, the interesting fact with simulations is that you can make really complex simulations. You know, I can complicate this model as much as I want to, but then the problem is you cannot easily identify what is the source of the issue. So we had a difficult balancing act. On the one hand, we wanted to have as realistic a representation of traders as possible, and we did have input from Oanda into this, because this is their job, they're a trading platform, so they have some insight, but at the same time we wanted to keep it simple enough so that we can actually study it and get some reasonable results or things that we can work with. But it's a very fine balancing act. But it's not the case that you can just throw different parameters and you can see the same patterns as you see in the real market, because you're not just checking one pattern, you're checking multiple patterns. And what we've done is we were able to replicate all of these patterns to a reasonable extent.
I think we've got time for one more question, sorry.
It is a quick one. You mentioned that improving your model traders by making them learn was not a strategy for improvement. Did you identify something that was a strategy for improvement?
Well, we've only worked with a couple of strategies that learn. So we have not exhausted the full range of machine learning algorithms that we can use. So it's not. I cannot generalize this result and say it's definitely not the case that you should learn in the market. So we need to do more work on that front. But it was quite telling that, for instance, genetic algorithms, they just wouldn't. The results were unexpected. We cannot identify exactly what is happening simply because of the complexity of the algorithm itself. And we need to do more work, and we need to run more experiments. But it was quite interesting, and that actually reflects some other results. Previous work in the literature that has demonstrated that it is not essential to have systems that can learn to be successful.
Okay, I think we're up for time, so thank you very, very much indeed. Fantastic.